Welcome to another Ocean Ideas Talk, brought to you by ocean lovers.
I am delighted now to welcome our next speaker, who is Tristan Salle. Tristan is going to be talking about going with the flow, exploration from the river to the ocean, and how the Earth's surface is like the living skin of our planet, connecting physical, chemical, and biological systems. Associate Professor Tristan Salle is an associate professor at Sydney University in the School of Geosciences and has worked on a diverse range of projects related to Earth surface processes. Please, would you join me in welcoming Tristan?
Okay. Hello, everyone. Does it work? Yeah. Yeah. Cool. Hello. Yeah. So, thank you for having me first. So, the idea of what I'm going to talk about today is about like how the biodiversity and how life has evolved over the last 540 million years. So I'm talking about like a long, long time. But maybe before starting this story, I'm going to give an overview of a timeline of Earth's history, basically. So Earth was created about like 4.5 billion years ago. And we have the apparition of life in the form of bacteria about like 3.5 to 4 million years ago, so billion years ago. Initially, these bacteria were really simple. We've got some forms of this that you can find, for example, in the Pilbaras in Australia. And we had to wait until the apparition of the atmosphere, the apparition of the ocean and plate tectonics to have new forms of life that evolves. First in the form of cyanobacteria, so a type of plankton we see at present. And this happened around like 2 billion years ago. And from 2 billion years ago up to, let's say, 500 million years ago, the evolution of life, of course, remained in the ocean, and there was not that much evolution up to the Ordovician, so that's a geological periods, which is called the Ordovician, which is about like 500 million years ago, where you see an explosion of life. And so the first explosion of life happened in the ocean, and soon after, about like 100 million years after that, you've got an explosion also on the continent. So my job consists in basically looking at what could be the reason for this explosion of life. And me, I'm more interested in like looking at continents, so looking at how the landscape is changing over time. So when I'm talking about landscape, I'm talking about how mountains are formed, how valleys in size, the continents, how sediment is transported from, let's say, mountains to the ocean, and how basically this could have a relationship with the evolution of life. So what we did initially was to try to develop a model that basically could represent this evolution over time. So when we think about the surface of the Earth, so I mean, yeah, and you mentioned that, Rob, during your introduction, I like to see it as a kind of the living skin of our planet. So if you want, the interior of our body will be the core of the Earth, the crust, the mantle, and the atmosphere will correspond basically to the ambient air that we've got. And so the skin, our skin, basically is reacting to what is happening in our body, but also to what is going on in the air that we've got around us. Similar things happen for the Earth. So if you think about the surface of the Earth, you've got the core, the mantle that is going to change basically and basically move plates around, and also you've got the atmosphere with different type of rain, different type of temperature, and this rain is going to drop, form rivers, and these rivers might erode sediment, transport sediments, and move these sediments across in different regions. Okay, so what we try to do is to try to see when we look back in time, so several hundred million years in time, how this evolution could have like changed for example, the amount of nutrients that you will find in the ocean, and how basically the change in landscape as it becomes more and more complex could basically create some specific niche for species to develop and adapt. So what we did was to basically use models that will integrate some understanding of the evolution of the precipitation or climates over the last 100 million years, looking at how plate tectonics has evolved, so how basically our different plates have moved over time, and trying to evaluate how this will have an effect on the surface of our planet. Okay? And when we did that, we specifically looked at river transport, and to go back to the analogy I made before with looking at the surface as the skin of our planet, we consider, I consider the rivers as like a circulatory system. Okay, so that will be when you carry sediments, you carry also nutrients, and these nutrients will help for the evolution of life. Okay, so taking these two into consideration, basically looking at how change in rivers and change in the amount of water and sediment that is carried by these rivers has evolved over time, we try to look at how basically it could have an effect on the evolution of marine life. So when we look at marine life in the past, here we've got some beautiful example at the back of a nice photography of marine life. When we look at in the past, obviously, like most of the ancient life has been destroyed. Okay? What we can rely on is fossil records. I mentioned the ones that you can find in the Pilbaras. You've got some old fossils that are still living today, such as stromatolites, for example. You find them also in Western Australia. And so you can have some clues in different places around the world of like specific organisms that were living at this specific time. It's a bit like a Cluedo, if you want to. You have like small clues here and there, and you can try to date these clues and try to get a sense of how life was at specific time. Okay, and so what we did was using these different clues that have been collected over, I don't know, 200 of years of fossil records, where people have been trying to map how the different families or species have evolved over time. So if we look at a curve like that, you will see that if we start like 500 million years ago, so pretty much there was only cyanobacteria as living life, okay? Then you've got like this big, huge increase in species diversification. This is what we call the Great Ordovician diversification event. So it happens between 500 and 400 million years ago. Then after you see a kind of a plateau, so it reached a kind of a threshold, and then after it stayed like this for about 250 million years ago. Then after you've got a big drop, okay, which corresponds to the time where you had like this massive continent, which is called the Pangaea, that started to break, okay? So you've got a big drop, and then after you can see an increase, a continuous increase up to the number of species families that we find today, okay? What we did was mapping against these numbers of families, okay, that we find in the past. We mapped the flux of sediments that was coming from the rivers, okay? And so when we do that and we combine the two curves together, so we look at them together on a graph, basically you can see that they are pretty much they have pretty much the same trend. So you see like an increase from 500 to 400 million years ago, when you've got this increase of species, and after you've got a plateau, then a drop, okay, and then an increase as well. So there is like a strong connection between how the biodiversity reacts to the amount of sediments that are carried by river. So this link, until like this studies that we made when was it, late last year, basically it was not something that was clearly identified. So what it means that there is basically a strong correlation between the evolution of life and the formation and the evolution of rivers. Rivers being driven by physical forces, so that will be like rain and plate tectonics. So what we suggest, and potentially if there is like biologists in the audience, there is one. Sorry. No, if there is biologists in the audience, they will say, "Oh wow, what is he saying?" We are basically saying that abiotic factors, so physical factors such as rain, tectonic, uplift, they are as equally important or even more important to the diversification of life than macroevolution or like biology, okay? And this is, for us, potentially one of the prime factors for the evolution of life. If you don't have basically the amount of sediments and nutrients that are provided to the ocean, the apparition of the diversification of life will not have happened. Okay, so that was the point of this research. So now I've got like a couple of minutes, so I'm going to just make a comparison with, put that in perspective with what we look at today. Basically, I think like the idea is that what we can learn from this type of research, which are like, like we are looking like really far back in time. How do you apply that to present day? So me, I don't, but basically it can give some clues. And the idea is that when we are thinking about like restoration or how to basically provide some ways of mitigating the impact of that we have on the biodiversity, we have to think of it, globally. It's not just like us. Okay, let's just look at this specific marine park and let's protect it. That's really good. But there is like interconnection between everything. And the links between all these things are super important, and it makes it even harder to really like make something that is going to be meaningful for the environment, because like there is all this interconnection between things. Okay, even if we were able to find, I don't know, a kind of a cement that will allow us to absorb more CO2 from the atmosphere than trees. Do you think it will be a good idea, to get rid of the Amazon to put this cement? No, okay, we will reduce the CO2, but there will be other implications, okay? So all this, I guess, put it in the reason why you invited me.
We've got time for one question.
Yeah, sure.
Any questions from the audience before we move on? Let me just grab a microphone.
In the ocean depends on flowing rivers, the sediments in rivers flowing to the ocean from the land. That seems a bit unusual for me.
Yeah, so when I say sediments here, so sediments obviously, but what is carried as well by rivers is nutrients. And the nutrients, basically, they are the basis for the evolution of life. If you think about the Great Barrier Reef, for example, there has been a lot of problem induced by farming. Okay, farming upland, you've got erosion, you've got rivers transporting the polluant to the ocean, and you've got corals that are dying. So exactly the same, in the same ways as you will transport polluant, you also transport nutrients.
I have to revise my biology because I thought life started in the sea and sort of went up onto the land. But
oh yeah. Oh no, yeah, exactly. I mean, you're right. Life started in the sea, and then after. Not so far after that, I mean, like complex life moved from the ocean to the continents. So it initially developed in the ocean, but nutrients were there. Nutrients, they are basically the constituent of rocks. In part of the rocks, you've got some nutrients like calcium. Many. So these nutrients, they are like the basis for the evolution of life, and they are not like a biological. Some of them are biologically based, but others are just like, rocks that you find on the surface of the Earth.
We are going to need to wrap things up there. Would you join me in thanking Associate Professor Tristan Salle?
Thanks for tuning in. We hope you enjoyed this episode of Ocean Ideas. Please make sure to share it with your networks and help us in our mission to turn ripples of action into waves of change for our blue planet.